And hello everyone, I'm Zedong from Southeast University in China. So today I'm very excited to share our recent research from the address block to the authorized prefixes and redesigning RPKI ROV with the hierarchical hashing scheme for fast and memory efficient validation. So as we know, the BGP is the backbone of global internet connectivity, serving as the de facto interdomain routing protocol. However, BP was proposed without any building mechanisms to ensure the security, making it vulnerable to prefix hijacks. And in recent years, several hijacking events has caused widespread consequences, leading to significant financial losses. So to address the vulnerability of the BGP, the RPKI is standardized by IETF, a security extension to BGP, and based on that, Route Origin Validation, or ROV, with the Route Origin Authorization, or ROA, is proposed to stop the prefix hijack. And ROA securely binds an IP prefix to their origin AS numbers, and ROV validates the BGP routes against ROA to check if to block the unauthorized claims. And there are three kinds of results: valid and invalid, and the not found. So here is a case where the ROV successfully stopped the prefix hijack. And so from this previous case, we can see that ROV is powerful. However, the data sourced from the ROVista shows that only 27% of ASICs have adopted the ROV after years of effort, and the adoption rate is growing slowly. So why is the low adoption rate since it's powerful? A longitudinal study in NDS 24 shows that the operational efficiency concern as one of the main barriers. And we further measure the validation speed of current ROV schemes for varying validation outcomes. And we found that the more the valid routes, the lower the validation speed. And the PowerPoint shows the current stage of the validation outcomes, and with the promotion of RPKI, the proportion of valid routes will increase as the future stage. So with the promotion of RPKI, the proportion of valid routes will increase at the future stage, so that makes the ROV efficiency issue become more severe in the future. So to address this efficiency concern, we analyze the performance botnet of current ROV schemes theoretically. But before that, let's take a look at current ROV schemes with address block. So ROV validates the BGP routes by verifying the origin of route prefix using ROAs. This ROA binds the address block to the AS numbers. Address block, which consists of the prefix and the max length, and contains all subprefixes, which consists of subprefix with prefix length not exceeding the max length. For example, an address block shown in this slide contains 3 authorized prefixes. So when the router receives the BGP routes, it checks 2 key fields. First is the route prefix, or the RP, and the route origin AS number, or the RO. The ROV validates them by comparing them to the ROA, yielding to 3 outcomes. So if no ROA covers this route, the result is not found. And an ROA covers the route means the RP is the subprefix of the ROA's prefix. And if at least one ROA matches the route, it is valid. And ROA matches the route means the ROA covers the route, and the route length, the prefix length is within the ROA's max length, and the RO matches the ROA's AS number. And if at least one ROA covers the route but no ROA matches it, it is invalid. So from this condition, we identified 2 key steps in ROV with address block. First, check if the ROA covers an RP. Then, if it's covered, verify if it matches the RP. And we modify the current ROV process as the address block model, and we build up a decision tree. And in this decision tree, EC finds an ROA covering the route, while CM checks if it matches the route. And the condition EC and CM may be checked alpha times to reach an ROV result. So from this decision tree, we can find that the validation for valid and invalid routes are complex. As the RPKI grows, the valid routes dominate, which slows the validation's speed and become a key performance bottleneck. So to overcome this bottleneck, we designed a new ROV model. And in this new model, EM means finding an ROA that matches the root. And since the new model operates at the authorized prefix level, the EM condition can be complete through exact matching. And at the same time, we place the EM condition at the top of the prefix tree to quickly validate this increasing number of valid roots. And EC retrains its role from the address block model, checking the ROA's coverage for the remaining case, any invalid or not found. So we prove that our new proposed authorized prefix model shares the same validation result from the address block model, and we validate at a faster speed. So due to the time limitation, for more details, please read our paper. And with this new ROV model design, we need to implement it in the real-world environment. And we identified key hurdles in implementing this new model. So the first is maintaining the ROA at the granularity of authorized prefix. So to address this, we adopt a bitmap-based encoding, which was previously presented in Infocom 22. And we start by splitting the IP prefix tree into a series of non-overlapping subtrees, each with a fifth height of 5. So after splitting, each prefix can be located in a specific subtree and with its fixed position. So this prefix can be identified by a subtree identifier, which is the root prefix of this subprefix, and the index, which is its node number in a level order traversal. Also, each subtree is represented by a subtree identifier and an encoded subtree, which is the bitmap of its authorized prefixes. And based on the previous method, we generate a bitmap-based encoding for the ROAs. We first calculate the subtree identifier for given authorized prefixes. Then we mark this bitmap based on their node index within its subtree. Finally, we combine the subtree identifier, the encoded subtree, and the AS number into the final ROA encoding. So with our bitmap encoding in place, how to validate these BGP roots with the bitmap-based ROAs? To achieve this, we propose a hierarchical hashing scheme with two hash tables, the SOT and the STT. We first talk about the subtree origin table, or SOT, to store the authorized prefixes with their corresponding AS numbers. So SOT use subtree identifier and the AS number as keys, with the encoded subtree as the value. For example, a prefix for ASX and ASY are encoded and stored as separate entries based on their distinct AS numbers. So with the SOT, the match condition can be conducted by a simple hash probe. We first compute the subtree identifier and the index of the root prefix. Then we get the encoded subtree by currying SOT with the identifier and the AS number as key. If the index bit is set, the result is valid, and the total process has the time complexity of O1. For example, when validating the BGP roots in this slide, we just compute its subtree identifier as 192.0.2.0/25, and the node index is 3. So we curry in the SOT and get a bitmap where the third bit is set. So we're confirming that the validation result is valid. And to handle the cover judgment, we designed the subtree table, or STT. Unlike SOT, STT stores all authorized prefixes without the AS number, using the subtree identifier as key and the merged encoded subtree as the value. So as the previous example, prefixes from ASX and SY are combined into one STT entry using an OR operation on their bitmaps. So with STT, the coverage operation uses the several hash probes. First, if the SOT match fails, we get the encoded subtree from STT using the subtree identifier as key. If a bit covering the RP is set, the result is invalid. And for example, when validating another route in these slides, and we can first check the SOT with the subtree identifier, and we found that the second bit of the retrieved bitmap is 0, so the match fails. And next, we query the STT with the subtree identifier. The bitmap shows the first bit is set, meaning that the node 1 in the prefix tree has the prefix that covers the node 2's prefix. Then, since this covered but not matched, the result is invalid. So in our previous example, the covering root prefix was found within the subtree, but what if it's outside? We need to find the covering prefix in the subtree using a line search, and this backtracking process has the time complexity of OL, where L is the prefix length. So this significantly slows the validation. And to solve this, we designed the optimized algorithm in IPv4 and IPv6. So in IPv4, we record all the coverage status for some key prefixes, and most prefixes can find the coverage status of O1 time complexity. And in IPv6, we use a binary search strategy with OL time complexity. So due to the time limitation, for more details, please read our paper. And with the previous methods, we developed the H-square ROV, a hierarchical hashing ROV scheme. We use the bitmap-based encoding scheme to maintain ROV at authorized prefix level, and we construct a hierarchical validation structure using 2 hash tables. The validation logic aligns with the authorized prefix model we mentioned before. So after designing the H-square ROV, how to integrate it in the software routers, and we minimize the modification to the routers as much as possible and verify the implementation with 2 software routers, which is FR routing and BIRD. And here is the origin BGP implementation in software routers. And we only need to modify 2 modules in the software router. First, augmenting the PDU handler with, to construct the ROA with bitmap encoding. And second, substituting the legacy Route Origin validator with H-square ROV's validator to boost the performance. And let's evaluate the H-square ROV's performance. Our experiments are conducted under the mentioned environment, comparing H-square ROV against schemes we named by their coded structure, which is LPFST and HT, HT plus PT, and Partica. So for validation speed, H-square ROV outperforms all schemes in the IPv4, and in IPv6, H-square ROV outperforms LPFST, HT, HT plus PT, but is lower than the Partica, showing room for further optimizations in IPv6. And we analyze the storage overhead required for loading real ROA data. And in IPv4, H-square ROV consumes the least memory, and in IPv6, H-square ROV uses the less memory than the HT plus PT and Partica, while more than the LPFST and the HT. However, H-square ROV achieves a combined memory consumption of 21.1 megabytes, exceeding the HT by just 0.2 megabytes and far below others. So finally, we emulate the additional delay caused by the ROV on BGP conference under updates burst on our emulation platform. We use 12 topologies, the top 100 consisting ASs from AS ranks top 100 and Korea's AS level network topology, and 10 generated topology with 1,000 ASs. And H-square ROV reduced the ROV-induced delays in BGP conference by the 13.4% to 64.7% compared to the other schemes. And in conclusion, the performance bottleneck of current ROV schemes lies in the ROV model using the address block. And to tackle this problem, we proposed a brand new ROV model based on the authorized prefixes. And we present the H-square ROV, which achieves fast and memory-efficient validation. And our system evaluation shows that H-square ROV considerably mitigates the ROV-induced routing coverage delay, so offering robust solutions. And for more details, please read our paper. And you have any questions, feel free to contact this email. And here is the link of our emulation platform and the source code. Thank you for your attention. I'm happy to take any questions.